Let me share the screen. Can everyone see it?
Yes.
Okay, perfect. So I'm Jing from Intuit AI and UC Davis. I'm here to present this data augmentation method for credit risk score. Credit risk score or credit scoring score are used to estimate the probability of default, aka not paying the money back in time every month. So it's a binary classification model based on the application materials. The scoring models help underwriters to tag potential bad customers and also improve their approval rates. Conventional credit scoring models use previous funded loans and their performance for training and test. However, this data is not a good representative of all the application because they are already pre-selected from old credit scoring models, which is supposed to have a low credit risk. So to address this sampling issue, we propose the semi-supervised learning method to augment the data set, which help it to be more representative of the through the door population. So from the data perspective, proof of funded applications are labeled with their actual performance, good or bad. Bad means default. And we also have another part of declined application, which have most of the features, the data available, which might have some missing parts which lead to their decline. So here's the general idea of a method called reject inference, a term mainly used in finance. This method follows the basic semi-supervised learning framework. The data given the observed is separate. On the left, you can see here, the colored one is the funded loans, and the gray part is the declined data. The model with only colored data is called no good or bad model. Traditionally, reject inference methods will inform all the declined population and use them to train the new credit scoring model called reject inference model. However, the big concern here is that it might introduce a part of data whose label are highly adapted and might be incorrect, which might impact the accuracy of the training set, and some of the data is not necessary to input into the training set. Therefore, we inform the labels of all the declined application, but only select part of them into the final training set. We propose two augmentation method here and also introduce a matrix to evaluate different credit scoring models. The first method is a self-training method with confidence model. So the core is still a self-training. It iteratively trained on both labeled data and the data just pseudo-labeled data in the previous iterations of the algorithm. It starts with this no good or bad model, the conventional one, and predict all the unlabeled data called right as unknown here. And then a confidence model is introduced to evaluate how trustful these predictions are. We have two options of confidence model that we'll introduce later. This confidence model will filter a small group of predictions that are trustworthy and put them into the training set. You can see that this confidence model is actually replaced the original prediction probability method to do this filter. So we try to introduce samples from both classes to the training set. And this new model is trained with this small augmented data. This process iterates with confidence models and it ends until no predictions are found or after certain numbers of runs. So the key variant between the conventional self-training is the confidence model. It evaluates the confidence of newly pseudo-labeled data. So we have two algorithms. The first one is the probability calibration. So for this base algorithm, say like credit scoring models, now we use more advanced ones than just a statistical model like linear regression. example, we use XGBoost. So this based algorithms tend to have some kind of probability distortion. XGBoost has a sigmoid shape one. So a large group of probabilities might cluster in a very small range. So we use isotonic regression to calibrate these probabilities and use the corrective ones so that they can do the cut better to select the most confidence predictions. So another algorithm we use is trust score. This is a work introduced in 2018 to evaluate the trustworthiness of predictions. It uses relative precisions of data in the feature space to measure the uncertainty of prediction. You can see it as an adaptation of KNN model in this case to evaluate, not to do the prediction. So if a newly labeled test point is close to the data of the same class and far away from data of other classes, I think the prediction is correct. The second data augmentation method we propose is weak supervision with snowcode data programming. Snowcode is a Stanford project which offers programming layer architecture to create the training sets with domain knowledge from their underlying generative models. So what we do is we created the weak classifiers about who might default from different sources, like from the lending policy team document, early exploration about the data set, domain knowledge from the interviews with underwriters and the policy team. Then we generated a label matrix of applications and labels. For each application, it will have multiple labels from every classifiers. If one classifier cannot make their decision on this application, the label will be none. So with this label matrix, Snowcode framework will generate labels for those unlabeled data. And what we did is we identify confidence ones from their prediction probabilities and augmented them into the training set. So here's an example about weak classifier will look like. When we talk about they are weak, we mean that they are not as powerful as attribute models. They just have a very basic roles. It can use different logic, multiple logic, and include different features. So to evaluate these credit scoring models, especially reject inference models, beyond AOC and the KS value, we introduce this approval rates. It measures the percentage of applications we could approve in the test set when keeping similar default rate or the bad rate according to the default possibility predicted by the credit scoring models. So first, why control the bad rates? When we approve more applications, there are larger chance that the bad applicants will also be funded. So if a model can distinguish the good and the bad customers better, is seen as a good model. So this is just an illustration about how exactly the calculation look like, the bad rate, approval rate, etc. First is what observed here. The red ones are the bad ones, and the bad rate is 2/12. Approval rate is the size of this group versus the number of overall data. Then reject inference model or credit scoring model, anyway, it predicts all this data points, their risk points, and rank them here from lowest to highest. So in this case, instead of predicting binary target, we list their probability here. Then we try to estimate a probability threshold that the application on the lower side, this side will be approved, and we can calculate the bad rate among this already labeled data. Then this matrix report when the bad rate is controlled to a very preset number, what's the maximum, the percentage of applications we could approve. So you can see that here we have two labels for the test. One is the original one and another is augmented one. It's because when we try to do a field evaluation for all the applications, we cannot just use previous funded loans for the bad rates. So we use external data sources to label the declined application and get an augmented test sets. So these new ones are all real labels. 30% of augmented test set are from this part. So we can see that it's hard to actually match every declined application. So in that case, we can only calculate the bad rate from this part. So the control bad rate is set in our environment to be lower than the industrial level that actual lending institutes can take normally. So with this, we can compare the approval rate among different credit scoring models. This measure provides direct business insight about approval and the risk control. For the model performance, self-training with calibrated probability outperformed the conventional model and the one traditional rejection inference method called fuzzy augmentation from AUC and the KS value. And the approval rate is lifted by 2% when the bad rate is controlled as 2.5%. This number is not very big, but it can mean large revenue difference since the market is very large. So the result of weak supervision is more mixed. The performance is the best when the approval rate on this approval rate when the controlled bad rate is larger. So from our analysis and best guess, it's partially due to how we design those weak classifiers from the domain knowledge. Most of them is designed to identify those bad applicants among relatively high credit risk applicants, rather than also consider what could be good ones in this small group. So besides from performance, we think weak supervision have high application opportunities due to the fact that it can co-star itself. So with only domain knowledge, snow codes and all other data programming method will help it to create the training set. Oops. For the takeaway, we propose two normal reject inference techniques to augment the data set. One use self-training with variant on the confidence model, and another use the idea of programming. So this also we introduce a new business-related measure to evaluate the performance of these models. Great, thank you. I'd like to take questions.
Thank you for the great presentation. We're just at time, but maybe we'll have time for one question. Anyone on the line? Okay, maybe I'll go again. So you've probably heard a lot about, the new or the fast growing field of fairness, right, in finance when it comes to especially credit lending and approval and rejection process. So this, and I understand that your study is more geared towards how can we better predict rejection, based on what we're seeing in the past. But can you think of how your models can potentially help not necessarily replicate what happens in the past, but also control for certain biases like bias against gender or race or certain age groups and so on?
Yeah, that's a problem we're working on right now because it is very hard to say like how the models will exclude the variables like genders and etc. For now, we don't have a very good solution at this point, but we are thinking about using one of the few like fairness techniques that presented in AAAI this year to see like, okay, how to say not just train a model, but to teach it a little bit more fair in the future.
Very nice. Thank you so much.
Yeah, but that's a very important field. Thank you for asking.